Here we are. Once again, Natural Science 116. This is the second video lecture, Natural Science 116 video lecture 2. I'm just going to keep numbering them and uploading them as soon as I make them. More about that later. So what are we talking about today? I ended the last lecture giving a list of topics that we had, and states of matter and phase transitions and entropy were what we were going to do. These are all pretty theoretical. Lots of concrete examples go with the subject nonetheless. But yeah, I have a little extra board here because I'm next door. And I want to start with a short discussion of energy units, just to clear things up once and for all. And then we'll go into the states of matter and so forth. And as always, make sure you take really good notes. Leave a lot of space in your notes. I'll give you ideas where you can look stuff up or homework assignments to figure things out as well. So you leave the space, you can come back and clarify. Yeah, here we go. So first of all, talking about energy units, we know that we're saying that energy is the capacity to do work. That's our working definition. Okay, capacity to do work. And we started out with the joule. Okay, so the joule, that's one unit of energy. In fact, we want that to be our major unit of energy. As soon as we did thermal physics, though, we have the calorie. Capital C was something completely different in its original definition, but then via the mechanical equivalent of heat, we found out that that is equal to 4,186 joules if you utilize friction or some other method. Okay. So the calorie, after all, is refers back to joules, which is, of course, the capacity to do work. Okay. I'll put the J up here as well. Yeah, so what other energy units are there? Then we talked about the kilowatt hour. Kilowatt hour. And by its definition, it could also be referred back to joules, because that was 10 to the 3, that's kilo, and a watt was a joule per second, and an hour was 3,600 seconds. So yeah, what did we have here? We had 3.6 times 10 to the 6 joules. So once again, we've got the energy conversion back to joules. Well, there are more units, and it could go on and on. But what's on your energy bill is the therm. The gas part of your energy bill, you pay so and so much for so and so many therms, okay? And that itself will be related to what's called the British thermal unit. So, British thermal unit which is BTU. Okay, so what about these? Let's make this a homework problem. Why don't you guys look up what's a therm, what's a British thermal unit, and then you can include it in this table here. So perhaps you should leave enough room here, leave some space, look this up. Let's call this homework problem. And then you can discover how many therms, British thermal units, correspond to what? Joules. Of course, there would be correspondence to calories as well. These are heat units. But yeah, so you can find out what are these conversions here. Okay. So homework problem, find definition of firm and British thermal unit. Because right, as soon as we learned about energy, we realized that it transfers from one form to another. So we had mechanical energy, we had thermal energy. That's what this mechanical equivalent of heat, that's why it's so important. Okay. Good, so that's a preface to what we're doing today. Go ahead and look these up. You can just put them in your notes that you turn in once you discover it, and then you'll be good to go. Good, so we've taken care of this topic. Now the next two and the third one, should we get there, are major. Good, so let's get started on those. Talk about states of matter first. States of matter. What are the states of matter? You guys take this on the road on your outreach. Probably talk a little bit about it. We're going to talk about solids and liquids and gases. Leave the plasma for some other time. Okay. So we're talking about solid, liquid, and gas, and we want to relate it to our energy discussion. So solid, and as an example, I'm using a block of ice. So I'm talking about water now, so there's our block of ice. And liquid, we've got a beaker full of water. Okay, so water. And then the gaseous state. How do I draw gas for water, going from ice to liquid water, and then maybe we'll just say we have a balloon here. There's a balloon, and there's the gas. So that would be water vapor, if you will. Okay, water vapor. Good, what does that have to do with energy? Well, if you apply heat to this ice, you will have eventually been able to turn it into water. So, you can just add heat here. If you add heat to the water, you can eventually vaporize it. What we're going to see in the discussion in a little bit is that we can talk about this as absorbing energy, and then we can reverse the arrows and have it releasing energy. So up here, we have energy absorption, and we're going from the solid to the liquid to the gaseous state of matter. And if we want to go from the vapor to the liquid, and if we want to go from the liquid to the solid, we have to be able to release the energy. So energy is absorbed. Well, instead of writing Q here, we'll say absorb energy, or absorb Q. How about that? Absorb Q. And then down here it will release. And in fact, the ice can be really cold. Say it's minus 30 degrees Celsius. And how would the ice absorb heat and remain ice? You could put it in a freezer that's at minus 5. Okay. So it would actually gradually go from minus 30 to minus 5 and on and on. Okay, so energy is flowing in here, flowing in here, flowing in here, and changing the matter from solid to liquid to gas. Okay, good. So So that much we have there. Maybe we'll put a note or two. So the substance absorbs energy until it changes state. And this change of state is what's referred to as a phase transition. So it's in its solid or liquid or gaseous phase, and the transition is from one to the other. And this is where we're going to find something unexpected. We're going to find something unexpected in the sense, in the terms of the energy absorption. Absorbs energy until it changes state. And once again, solid to liquid to gas. And the process can be reversed. Then substance releases energy and goes from a gas to a solid back to, got that wrong here, gas to a liquid back to a solid. So that's the overview. So you have that there. You've got the absorption on the one hand, and you've got the energy being released. Now what I'm going to do next, after I erase all these boards, is discuss at length a really stereotypical graph that you'll find in all the books and elsewhere that quantifies all of these things for water. So we're going to, this was, I didn't have any numbers here, right? So I'm going to quantify it, and you'll see some interesting features going on. So states of matter, the absorption. So let me go ahead and erase everything here, and then keep on going. Yeah, so let's talk about this graph here. Make a big one. This is a full width of the pager, okay? So we have a temperature axis. This is T in degrees Celsius. And leaving some room underneath, we have an energy axis. So this is Q in joules. Make it even wider. Make it even a little bit wider. Got a lot to say here. Okay, so Q in joules. And what we're doing here is adding heat to 1 kilogram of ice. Okay, so we're adding heat, which is just energy. We can talk about it in joules. So 1 kilogram of ice, and we're going to start out. Let me make a scale here: 20, 40, 60, 80, 100. So there's 20, and there's 40, 60. Good. So 100 is this one, and we'll have minus 20 degrees Celsius. If we're going to go ahead and let the ice start out at minus 20 degrees Celsius. So here we go. At a kilogram of ice, minus 20 degrees Celsius. There's our block of ice. It's got a thermometer, minus 20 degrees Celsius. Good. There's our cartoon. And what we're going to do is consider what happens as you gradually add heat to that kilogram of ice. Well, what is going to happen is that the ice warms up, but it doesn't melt yet. Like I said, if I had it at -20 and I turned the dial on the freezer to -2, it's just going to gradually get warmer, but it'll still be a block of ice. So that's what we're going to consider up to here, where the ice actually reaches 0 degrees Celsius and it's still a block of ice. It's a block just hovering on, the boundary, 0 degrees Celsius. So this was 1, and this here is 2, and what we're talking about is we're heat the ice to 0 degrees Celsius. So we started with ice at -20 degrees Celsius. So we heat the ice to 0 degrees Celsius, and we even know, you guys have looked this up online, I've talked about it, Q is equal to M, specific heat of ice, delta T, and we'd have the numbers, a kilogram specific heat of ice, 20 degrees, okay, that would tell us how many joules the ice had absorbed. Okay. Now what happens is, we could say this is unexpected, because if we do this slowly enough, the ice will just gradually absorb energy and not change its temperature. So what is happening while the ice is absorbing energy and staying at 0 degrees? That's why this horizontal line is so important. Okay? 0 degrees, horizontal line, 0 degrees is 1, 2, 3. I'll label that right here. It's melting, but it is melting without changing its temperature. And what is kind of astounding is how much energy it takes to melt this ice. Okay. So what is this energy amount here on my axis in joules? How many joules is that? Okay. L sub F, oh actually I'm going to write this, Q melt equals L M L sub F. And this is what's called, this L sub F is the latent heat of fusion. L sub F, we write this out, latent heat of fusion, L sub F, 3.33 times 10 to the 5 joules per kilogram. Okay. Melting. So Q equals M L sub F. M L sub F. By the way, I'm going to turn this into a nice little homework problem. Okay, so everything's going to be on the board. I'm just going to supply the answer. So that was the melting. Yeah, what happens when this water is now completely liquid and it's still 0 degrees Celsius? That's some cold water. Then if we keep adding energy, it will increase in temperature. So we're going to keep adding energy now, 20, 40, 60, 80, 100 right here. So we're going to keep adding energy till we get up to 100 degrees Celsius. And this here I'll call 4. We're going to heat the water, and what's our formula here? Q equals MC delta T. So this was the specific heat of ice, this is specific heat of water. Okay. So now the water has reached 100 degrees Celsius boiling temperature, and what happens then? It vaporizes and it keeps the same temperature, so it's going to vaporize at 100 degrees Celsius, And in fact, this graph has to be broken down because it goes so far. And same here, that means we're interrupting that graph. And this here, Q sub vaporized, I'll write Q sub vapor equals MLF. And this is the latent heat of fusion. Okay, once I have all these definitions down, I can talk about them with it having it all up on board. Latent heat of fusion, latent heat of fusion. Can I write that more clearly? Maybe, but only maybe. Okay, latent heat of fusion. And this fusion, okay, vaporization. Vaporization. Latent heat of vaporization, L sub V, 2.26 times 10 to the 6 joules per kilogram. Okay, M's are masses. Okay, now we've got a pretty complete set of things up here. And I can go ahead and I can take it through systematically once again. So we started with our block of ice. It's a block of ice in the freezer. We turn the dial up gradually. The ice absorbs energy and becomes warmer. It reaches 0 Celsius, 32 Fahrenheit. Next, we keep heating it up very gradually, but the temperature doesn't change. So we're not actually heating it up, we're putting energy into it, but what it does do is it melts. So that's the phase transition. Melting is the phase transition. The change of state happens, enormous amount of energy is absorbed to make that change of state happen. This is quite a bit of energy. This is 3/4 of the energy required to bring a liter of water to boiling, okay, which we know is a lot of energy. Watch the pot never boils, right? Okay, latent heat of fusion gives us that energy change for the phase change. Energy amount of the phase change. Okay, so finally that phase change has taken place. We've got a bucket of water. We're adding heat to it. It increases in temperature till it's ready to boil. Okay. And that was standard. We've been talking about that. But now if we want to vaporize it, so the liquid to the gas phase is happening here, and this enormous amount of energy, latent heat of vaporization, is required to turn the water to steam, or actually just to water vapor, vaporize it. So yeah, this graph, if you look this up elsewhere, you'll find this very self-same graph. It's so important because these phase transitions are major energy users, so to speak. Energy is involved in a great way. Okay, so that's why this is so important. So this here was the phase transition. Phase transition, solid to liquid. And it involves this much energy, right here. And then this here was also the phase transition. And it was the liquid to gas. You can write that down. Latent heat of vaporization. So how can I turn this whole thing into a nice homework problem? Homework problem. Well, since I put all of these numbers on here and I said it was 1 kilogram of ice for your homework, and you just want to actually want to leave some space right here. So when I write homework problem, just leave some space in your notes, figure it out, and put it right in there. Okay, this will be nice. I'll basically get started I'll start it with you right now. Okay? You can just have to plug some numbers in. Yeah, the homework problem is, how many joules was this? From here all the way up to here. To here. So how many joules from the beginning here, star, to the end here, double star? How many joules of energy did it take to do this heating and phase transforming? Good. Let me erase this so I have some room on the board. I'll formulate that and we'll get started. Okay. So let's just call this homework. How many joules from star to double star? And that's what I'm talking about. This point on the graph and this point on the graph. And the answer is Q total equals Q of, right, this meter. Try this again. We've got room. Okay, Q total equals Q of melt ice plus Q up. Once more, Q of heat the ice plus Q of melt the ice, there we go, plus Q of heat the water plus Q of vaporize the water. Okay, so there were 4 sections here, 1, 2, 3, 4, and you just want to add them all up and get the total. Okay, so let's even get started on that. Erase some of this here, but you have it. Available equals Q to heat the ice was the mass of the ice, the specific heat of the ice, times the delta T, which was 20 degrees. 0 degrees Celsius minus negative 20 degrees Celsius. That was MC delta T. And then plus M, latent heat of fusion of the ice, is our second one, plus M. And what is the mass here? I said it's 1 kilogram, so that's as easy as it can be. M, specific heat of water. And what's the delta T for the specific heat of water? 100 degrees Celsius minus 0 degrees Celsius. And finally, the water's been heated and it's going to vaporize, and then plus M, latent heat of vaporization of the water. So you add those 4 numbers up, you get some big number. And of course, you know, the number, fine, you do the number. The formula is actually better, keep it in abstract form, because then anytime you plug in any number here, you get that amount. You know, and also, what about out in nature? We may not be vaporizing things, but we could be using this half, heating ice and melting ice. Suppose you wanted to know how much energy it takes to melt a glacier. Okay, this will just scale up, big numbers, powers of 10. You could be melting a glacier, you could be melting the Greenland ice cap. You know, the volume of the Greenland ice cap, and figure out how much energy it's going to take to heat it and melt it. So you see, for environmental studies, people have to know this type of thing too. Okay, so it's full of practical applications in space transitions. Okay, so that's the very technical board here, but also very important and practical. Now we're hoping that the Greenland ice sheet, even if it were to warm up and melt, we don't want it to boil and vaporize too. Okay, that's a little too much of a good thing. Okay, but yeah, heat it up and melt it. you can use these formulas and figure out that number of joules just as easy as my homework problem here. Okay. There you go. Okay, now I have one more very important application to all of this phase transition material. And I don't know if we're going to get to entropy. We'll see how far we get. But let me erase all of this and just keep it in mind. So during this season, those of us in the Fresno area, Visalia, etc., we've heard about the orchards being flooded during a freeze. Why would the ranchers, the people down there in Orange Grove, Orange Cove, Visalia, why would they flood their citrus orchards in the winter when the freezing air comes in? Okay. Stay tuned. Okay, let's have a look here. So I'm going to call this phase transitions example flooding the citrus groves. Flooding the citrus during a freeze. With a question mark here. I've actually seen it. I've driven around in the winter and sky, clear day, bunch of ice, you know, sky blue sky, clear day, very cold, bunch of ice on the ground in the orchards. Okay. I didn't see it in Visalia. I saw it up around the Dare ones. Okay. So what's going on there is the following. And remember this. Here's our cartoon for the direction that energy flows. THTCQ. Energy flows from hot to cold. So why are we flooding the orchards, orange, lemon, what have you, in the winter during a freeze? Here's my picture. So here is our tree. And okay, it's got oranges hanging all over it. Okay. There's an orange tree. There's the ground level. And here is water. Here's a puddle of water. Water at 0 degrees Celsius. Just ready to freeze. The water's at 0 degrees Celsius. Here's the idea. We've got cold air coming in from the range, maybe coming out of Sequoia, Kings Canyon, down into the groves. So this is supposedly had cold air at, I'm just going to make up a number, minus 4 degrees Celsius. It's got to be cold enough to damage the crop. Cold air coming in here. And we've got water at 0 degrees Celsius. What's colder? The minus 4 degrees Celsius is colder. Okay, so we've got this minus 4. We've got this 0, and which way does the heat flow? It flows from warmer to colder, so it's flowing from 0 to minus 4. So yes, you're not going to warm your hands over a puddle of freezing water, but what is the heat going to do that's flowing out of this water as the water freezes, okay? This enormous amount of energy there, Q equals mass of water, latent heat of fusion of water. The idea is it's going to raise the temperature of this air from, say, minus 4 to minus 1. Something enough to avert the deep freeze, so the energy is flowing out of this water as it freezes, and there's quite a bit. There's enough energy to flow out as it freezes pretty much to boil water. a lot of energy flows out and heats the air. So air is heated to, and I'll just say -1 degrees Celsius, comma, save the crop from being destroyed by a deep freeze. So that's an example of energy flowing from hotter to colder. Even though that hotter temperature is actually ice water, and raising the temperature, came in at -4, let's say it gets heated up to -1, that's enough to avoid deep freezing the crop. Done deal, okay. So that's our big example of local validity and local interest. Flooding the citrus orchards. During a freeze. Citrus orchards. Okay, phase transition, right there. Very practical example. You can even look this up now. Now that you've heard about it, maybe look it up and see what someone else has to say about it. Okay. I was wondering if there would be some good images. Actually, excellent homework. Images. For this, you could find a good picture that, if I could have taken a picture of it back when I saw it up there in Madeira. But maybe you'll find something and you put in your book that's a very nice example. And it takes a little bit of understanding, right? There's quite a bit of sophistication here to know why is that working? Why is this water that is cold as can be still giving off enough energy to save a citrus crop? And once again, the answer is because the water is giving it off at 0 degrees Celsius, but the air is maybe -4. Okay, and that's enough energy in there to make the air a bit warmer. Okay, good. I'm going to erase this, and I think I have some time for the entropy topic too. Start the entropy today. I want to make some progress here. So far though, what do we have for homework? Working backwards. We had pictures for the citrus. And at the very beginning I had the idea of just some conversions, some energy conversions. These are all things that you can fill into your book, and then we have that calculation. You can fill into your notes, fill into your book, especially any nice images you find for this, definitely print them out, put them in your book. Okay. Okay, finally, entropy. This is a very theoretical topic in terms of what we're doing here. So entropy and the change of state. So we already saw that the change of state involves energy. Change of state involves energy. That's what we just saw. What else is going on? What else is going on? Or how could we say, okay, I have ice here, and then I have a beaker full of water, liquid water. Okay, so what else could characterize this solid-liquid transition? And what we could say is the ice is ordered and the water is disordered. Because here every molecule knows its place, so to speak. It's fixed. Here they can swim around. And if we go from water to, there's our cartoon, to gas, we can say it's more disordered. So this is the order axis. order, or actually it's the disorder axis. If you're going to have the arrow in this direction, it's the disorder axis. And when would things be the most ordered whatsoever? At 0 Kelvin, right? Everything's locked into place, but ice is ordered, water's disordered, gas is even more disordered. So what we say is this entropy, it's a measure of the disorder, a measure of, we could say, molecular disorder. A measure of disorder, and I'll put molecular here to indicate what we're referring to. A measure of disorder. So that's our entropy. And you can see that in phase transitions, it's very clear. Ordered, less ordered, more disordered, more disordered. It also works in heat transfer. Okay. So change of state, so far I did it in terms of phase change, or change of state or change of phase. So let me erase this forward. We'll do it also in terms of heat transfer, and you'll see the same thing. Entropy, so the first one I just did was phase change. That's what I just did here. Next thing we'll talk about heat transfer. Heat transfer. Yeah, so where's our cartoon for heat transfer? TH, Q, TC. Say we have conduction. So if we have conduction, you know, I like that cartoon of I have a wire or something, and I have a candle here in this class. Candles are butter candles, right? Anybody make that butter candle? Butter candle. Okay, so in the conduction example, right, the candle's heating up this, and this is just a metal wire. So it's hotter on this side. If you look inside, the molecules are agitated. They're moving faster. So the molecules are more disordered, and that disorder is spreading, so gradually the heat goes on to here. But if this end was cold at first, it was more ordered. And then, so the heat conduction, you can also see that the direction of the heat conduction corresponds to the direction in which the disorder is increasing. So the direction of heat transfer is the direction of disorder increasing as well. Okay. So the disorder increases as you do a phase change, but you don't even have to do a phase change. As the heat is transferring, that's the direction, and this corresponds to disorder increasing. Okay. So you got the heat transfer example as well, conduction, and it'll work with convection and radiation the same way. So I'll leave this here, and let me see, I'm going to find something to end this with. We have, yeah, so by the way, this was just qualitative right now. Now I'm going to get a mathematical expression for the change of entropy. The change of entropy, we're going to call it delta S is equal to Q over T. That's a strange expression here. It is units of joules per Kelvin because T is measured in Kelvin. Q, joules, of course. So the idea is this. Let me erase this and we'll wrap this up. Well, actually, we've got plenty of time, but I'll make it too long. Okay. So there's my definition, and the definition involves not entropy without change, but the change of entropy, so we always have a delta S here. Once again, T, and imagine heat energy flowing into something at T here, okay? So heat flows in, so heat flows in, then we have delta S equals Q over T is positive. Heat flows in, disorder increases. Okay, just like I had in my example a minute ago. If the heat flows out, then we would say delta S equals Q over T is negative. So I can say this, it would be the absolute value of Q flowing in over T is positive, and this one here, I could say equals minus absolute value of T, and it's negative, okay. Okay. So I'm going to give an example for this. Obviously, this is getting pretty abstract here because we're just talking about anything, right? Heat flowing into anything. But I have a good example for us. And the system, it's an abstract system, but we'll make concrete examples in a minute. Example, we're going to look at an isolated system. And we're going to have a TH and a TC. Okay. And when I say isolated, we've got a hotter and a colder object, and we've just locked the thing up in a cooler. Put the lid down, isolated. Okay, that's the idea. Got an isolated system. And delta S total now is going to be equal to the minus Q, by the way, there's a Q right there, minus Q over TH, because heat is flowing out, so there's a negative one. Heat is flowing out of the TH side, and it's flowing into the TC side, okay. So, I'm going to evaluate this thing here. I'm going to evaluate this expression, and we'll practically get a new law of nature. So this is one that really delivers. Okay? All we had was we took a hot and a cold object, put them in a cooler, closed the lid, leave them alone. Right? This one is losing some heat. This one is gaining some heat, but it's all closed off. There's the delta S total for this system. Delta S total. Now I'm just going to do some algebra on it. I'm going to pull out the Q. Absolute value, that's a positive number. Then I'm going to have 1 over TC minus 1 over TH. Just rearrange these guys. And to even make it more clear, Q, I'll do a common denominator. You guys remember that? So that would be TH minus TC over TC times TH. Delta S total. And we're going to look at this thing. Put a box around it. Here's the thing. These are Kelvin degrees. They're all positive. So the denominator is just a number. The numerator is TH minus TC. The numerator is itself always positive. Okay? This could be 50 degrees minus 40 degrees. Okay? This could be, 0 degrees minus negative 10. It's always going to be, take that back, erase the tape. These are one takes. I can't erase this tape. I am not editing these things at all. Let it be said. Okay, the negative temperatures example was just forget it. These are Kelvin degrees. Note all T greater than 0 in Kelvin. But the point is, of course, even stronger. Always positive. This thing is always positive. So delta S total is always positive when energy flows from hot to cold. That's a law of nature. And this thing can be formulated as a law of nature. We can say an isolated system, for an isolated system, the entropy always increases. Always. The best case is it doesn't change at all, but the entropy always increases, and that is as essential as heat flowing from hot to cold. The only way this entropy law is violated is if you run a movie backwards, then it looks like it's violated. Otherwise, the energy is always flowing from hot to cold. So that's as far as I wanted to get, and it's a longer lecture. Well, this will be coming up on an hour. I don't intend them to be too long because I want you to be able to, watch the thing, take your notes, and then review them and watch it again and say, okay. But we're still under an hour, so that's fine. But good, I'm going to formulate this now. We got through pretty nicely. This is a great place to have made it to. So let me just start adding some notes to this. Big star here because it's so important. So star delta S total is greater than or equal to 0. Is equivalent to energy flowing from hot to cold. So it's equivalent, and that's why we can call this a law of nature, because energy always is going to have to flow from hot to cold in an isolated system. That we're not going to get many arguments about that, are we? Okay, so delta S greater than equivalent to heat flowing from pH to TC. And you know what? I'm going to end with the laws of thermodynamics now. Now we've gotten to a point where we can formulate both of them, and then we'll have reached a good point here. Then we'll call it a day. All right. First and second laws of thermodynamics. The first law of thermodynamics, we've had it before, I probably didn't state it this way yet, and that is simply the law of conservation of energy. Right? Energy is neither created nor destroyed, it changes form. We'll call that the first law of thermodynamics. Conservation of energy. Conservation of energy. Check. But now we've obtained the second law. This one we're going to thermodynamics. So the second law of thermodynamics, I'm going to formulate pretty much just as I'm erasing right under here, but make sure you have it in your notes. The entropy delta S total of an isolated system increases. That's it. Entropy of an isolated system increases, and you can use as the limit that stays constant, but you know it's never going to decrease. Entropy of an isolated system increases, and the example here is going to be what I just had. So we'll make our cartoon this TC Q flowing here. And for this isolated system, delta S total.
Yeah.
Hold on. Actually, come on in. I'm giving a lecture. Delta S total greater than or equal to 0. Because I'm about to end it right this minute.
Okay.
Hey, don't interrupt me. Ricky. Hey, how you doing? Good. See, I'm doing these video lectures. Okay, this is the end of our Natural Science 116 video lecture 2. Went on long enough. Do your homework, take good notes, and see you later.